The ratio test is used when you have some really specific patterns you see in the series. And so the nice thing about the ratio test is it really kind of speaks to this non-increasing characteristic of the series. So if we look at this, the ratio test is saying take the next term and divide it by the term before. And if that ratio is less than 1, in other words, if this is a non-increasing term, then you have absolute convergence. And if it's greater than 1, that means an plus 1 is greater than an. If that ratio is bigger than 1, right? So for the divergence, if we're going to have subsequently larger and larger terms that we're adding to the sum, that sum is going to end up being infinitely large. So if we have a ratio, then it's greater than 1. Anything greater than 1, then we're going to have an infinite sum. So this ratio could be 1, this ratio could be 2, this ratio could be 7 halves, or this ratio could be infinite in value itself. Then we have a divergent series. And then if the ratio equals 1 specifically, then we have that inconclusive aspect coming through again. And all that means is that we need to pick another test. And I think I've said that many times now throughout the course of this unit, that sometimes we just get inconclusive results. And so this is saying that, really we don't see any fluctuation in the value in either direction. So have we reached a sum or haven't we reached a sum? We just don't know. And that's finite. So we need to pick another test. So that's kind of how the ratio test works. If we just kind of look at an example of two tests, and just try to misapply the ratio test to show kind of it's where it kind of breaks apart. Let's take a look at, we always kind of come back to these p-series terms, right? We've got this p-series term 1 over n as n goes from 1 to infinity. And we know that's divergent, so let's just kind of in brackets here. We know p equals 1. We know that's divergent. The p-series is the correct test to do. Likewise, if we look at 1 over n squared, also p-series, from n equals 1 to infinity, we know the p-series test is the appropriate test. We know, I put something wrong there, p equals 2. We know p equals 2 here, so we know we have a convergent series. Again, doing the p-series is the correct test to do. But let's try the ratio test with these, just to show you that inconclusive nature. So in other words, we take the ratio here, limit as n approaches infinity, of the next term, the n plus 1 term, so that's 1 over n plus 1, over 1 over n. And so we go ahead and evaluate this algebraically. Limit as n approaches infinity of 1 over n plus 1 times n over 1. Go ahead and just algebraically change that to multiplication. And so we have n over n plus 1. So we have to evaluate that as n goes to infinity. So we acknowledge that that is a indeterminate form, infinity over infinity. And so I'm just going to go ahead and do a little L'Hopital's on that. And go ahead and get the limit as n approaches infinity. Derivative of n is 1. Derivative of n plus 1 is 1. So we get a value of 1 here. We know it's a divergent series, but we get this value for the limit of 1. So And the absolute value means we could also do this with an alternating series. We just need to take that alternator off. So let's come back and look at this one. So let's try to zoom out here so we can get the whole page here. So let's come back then and look at the 1 over n squared scenario. So we take the limit as n approaches infinity of 1 over n plus 1 quantity squared over 1 over n squared. So that's the limit as n goes to infinity of 1 over n plus 1 quantity squared times n squared over 1. And so evaluating that limit, we're looking at n squared over, this is a polynomial, right? So I'll go ahead and expand it, n squared plus 2n plus 1. So we're looking at evaluating that limit. We could do L'Hopital's twice, or we could divide by the highest power of n. I'm going to go ahead and divide by the highest power of n just for kicks and giggles here. So the highest power of n is n squared. So I'm going to go ahead and multiply by 1 over n squared, and let's go ahead and clone that and squeeze that right here. Kind of scooch this over a little bit. There we go. So I'm going to go ahead and multiply by 1 over n squared there. Okay, so we're looking at then, this is 1, so the limit as n goes to infinity of 1 over, and we've got n squared over n squared, that's 1. 2n over n squared is 2 over n, and 1 times 1 over n squared is 1 over n squared. So we're looking at evaluating the limit there. As n goes to infinity, this goes to 0, this goes to 0, so we have 1 over 1. So here is the situation where when we took the limit as n goes to infinity of the n plus 1 term over the nth term, we also get a value of 1 for a converging series. So we got a value of 1 for a divergent series, we got a value of 1 for a convergent series. If we need to distinguish between convergent and divergent, we can't get the same values when we evaluate the limit. So since we're getting the same results for different situations, in other words, the same results for convergence that we do for divergence, we have to declare that getting a value of 1 is inconclusive. We've got to rule that out as a possibility to determine convergence or divergence. So that's the reason why we have this statement up here that when we get a ratio of 1, we have to pick another test. So when do we use the ratio test? I mean, here is a situation in this example here. These were obviously p-series. They should be a p-series test because they fit that description of 1 over n to the p. So this, we look for this form for a p-series. What do we look at? What form do we look for to do the ratio test? And so the forms we look at are things like a number to a power. So 2 to the n power, because 2 to the n plus 1 power is just one more multiple of 2 put into the product. And those have a nice canceling effect. So like 2 to the n power, or what I would just say is a number to the n power, is a good characteristic of using the ratio test. Also factorials, because again we have that canceling effect. N plus, when we have something like n plus 1 factorial over n factorial, we have some nice canceling to get rid of that factorial. just like if we have 2 to the n plus 1 over 2 to the n, we have a nice canceling effect that gets rid of the powers. So these are all characteristics that we should look for in order to tell us that we should be using a ratio test, because we get some really nice canceling. So when we look at this series, n goes from 1 to infinity of n cubed over 2 to the n, we see this first characteristic here. So I'm going to go ahead then and just kind of set up, and the ratio test, since we are doing a lot of times, you know, these series themselves are fractions, so a lot of times doing fraction divided by fraction. So we do a lot of inverting and multiplying. So my a sub n term looks like n cubed over 2n. My a n plus 1 term looks like putting n plus 1 in for everything. So n plus 1 cubed over 2 to the n plus 1. And so I know I need to do this divided by that. And so limit as n goes to infinity of n plus 1 cubed over 2 to the n plus 1 all over n cubed over 2 to the n. And eventually, starting with the next example, I'm just going to kind of cut to the chase here and go ahead and write that ratio as a multiplication expression where we multiply by the reciprocal. So from this point forward, I'm going to jump to this step right here. See the reciprocal here? It's the reciprocal of that denominator. And so now we can go ahead and cancel. So if we think about this, this is, you know, if we just let n, let's just pretend for a minute that n equals 8. This is 2 to the 8th power. This is 2 to the 9th power. We have one extra 2 in the denominator. So when that, and that's the nice aspect about the ratio test, is we get that canceling of powers. So this then is n plus 1 cubed over 2 times n cubed. And so looking at that, there we go. I'm going to go ahead and I'll do, well, you could do L'Hopital's, you could FOIL that out. I'm going to go ahead and I'll do L'Hopital's. Shouldn't be that hard to decide, but we'll go ahead and do L'Hopital's here. So we get the limit as n goes to infinity, taking the derivative of the top, that's 3n plus 1 squared, times the derivative of the inside, which is times 1. So I won't even put that in. Derivative of the bottom, 6n squared. Gotta do L'Hopital's again. Oops. Okay, so we're going to do L'Hopital's again. Limit as n goes to infinity of taking the derivative of the top, that's bring the 2 down, so it becomes 6 times n plus 1 to the first power, times the derivative of the inside, which is just 1, over, bring the 2 down, 12n, and then L'Hopital's just one more time. Or we could divide by the highest power of n at any time you feel like expanding that numerator. So here would be 6 times the derivative of in here, which is just 1. Derivative of 12n is just 12. So we get a value of 1/2. So if we notice, we have the value is less than 1. So we see that the limit, so at this point we can say basically that we get this value which we know is less than 1, and so we can say then that this series of n cubed over 2 to the n, I think that's what it is, right? Yeah, n cubed over 2 to the n. The series n cubed over 2 to the n converges because of the ratio test. So for this series here, we've got n times the quantity of 3/2 to the n power. Again, we see this this characteristic that we have, and if we just kind of come back here and let's just kind of bring this stuff with us, the characteristics of the ratio test. Okay, so we'll put that right there. So there are our characteristics of the ratio test. We can see that we have a number to a power here. It looks kind of geometric series-ish, but we have this n out in front. We don't have a constant here. You know, geometric series look like a r to the n, and we have an r to the n, but we don't have a constant out here. We have a value that changes with every term that we write. So where this is a geometric series, just to kind of preview, this is what we call a power series. A little bit different because we have this power factor out front here. So that's just kind of a preview of what we're going to kind of get into in the next unit. So we've got this characteristic though, we have a number to a power. This number is 1.5 to a power, so we definitely want to use the ratio test. So we have the limit as n approaches infinity, and like I said, I'm going to go ahead and cut to the chase and make the ratio a n plus 1 times 1 over a to the n, multiplying by that reciprocal. So the n plus 1 term looks like n plus 1 times 3/2 to the n plus 1, and then actually I take that back. I think I am going to write it as a fraction because I think it might work a little better. So my mistake. And then over the a sub n term, which looks like n times 3/2 to the n power. And so as we're evaluating this, this is kind of how I like to think about it. Kind of helps you see where things are canceling. N plus 1 over n doesn't cancel, so we're going to keep that. And so then you got to ask yourself, where do I have more 3/2 fractions, here or there? So when we look at this, we have n of them here, and we have one more up here. So that means we need to leave one more up there in the top after the canceling occurs. So we have something that looks like this. So we're evaluating the limit as n goes to infinity of, I'm going to go ahead and multiply through 3n over 2 plus 3/2 over n. And I'm going to go ahead and do L'Hopital's on here. So limit as n goes to infinity, derivative of 3/2 n is 3/2, derivative of 3/2 is 0 over 1. And so 3/2 over 1 is 3/2. So that happens to be larger than 1. So in other words, our terms are getting bigger as we write them and add them to the sum. So we know the sum is eventually going to become infinite. So this diverges because of the ratio test. In this example, if we notice, if we kind of get those characteristics back here, there we go, as to whether or not we should be looking to use the ratio test. If you notice, we have a factorial in this. We also have a number to a power. That number just seems to be, just appears to be changing along with its power. But we have the factorial there, so definitely a candidate for the ratio test. So I think this one I'm going to be able to write in reciprocal form right away. So let's just kind of say, let's kind of set this up. The a sub n term looks like n to the n power over n factorial. The a to the n plus 1 term looks like n plus 1 to the n plus 1 factorial over n, n to the 1 to n plus 1 to the n plus 1 power over n plus 1 factorial. I said that wrong. So if we take the limit as n goes to infinity, we're looking at this times the reciprocal of that. That's kind of what we're looking at. So we're looking at a to the n plus 1 times the reciprocal of a to the n. So we're just using some algebra to change that from a division of two fractions to a multiplication of two fractions. So we have n plus 1 to the n plus 1 power over n plus 1 factorial. And that's times, then we take the reciprocal of this, n factorial over n to the n. So that's what we're finding the limit of. And so as we look at that and simplify it algebraically, we can think of this, let's just kind of rearrange this, n plus 1 to the n plus 1 power. And I'm going to put that over the other thing that's raised to a power. So I'm kind of pairing up like expressions. And then we have n factorial over n plus 1 factorial. So if we take a look at, what this means in terms of canceling, we can think of this as like 5 factorial over 6 factorial. So we're talking about 5 times 4 times 3 times 2 times 1. We're talking about 6 times 5 times 4 times 3 times 2 times 1. So if we're looking at canceling, then we see that everything cancels top to bottom except for that first term, the 6. So the 6 is that the 6 is that n plus 1 expression, the 5 is the n expression. So this whole thing reduces to 1 over n plus 1. And so we have n plus 1 to the n plus 1 power over n to the n power times n plus 1. So if we have some more simplifying to do, and we have to take a limit that as that goes to infinity, because we have the term n plus 1 here, that's like our 6, and n plus 1 here, and this is, we can think of as n plus 1 to the first power. So we have an n plus 1 down here, we have n plus 1, n plus 1's up here. In other words, we have n more. So to simplify that, we can take the limit as n goes to infinity, and that is then n plus 1 to the n power over n to the n power. So that's how that simplifies. And so this gets tricky because L'Hopital's isn't going to work, because how do we reduce, how do we do L'Hopital's n times? So this is definitely a divide by the biggest power of n. In other words, I'm going to have to divide by n to the n power. That's the biggest power of n. So it's just algebra, nothing more than that. So I'm going to go ahead and do that. Limit to the n, limit as n goes to infinity. And so let me get my upper and lower expression set up here. So let's take this one first. I'm going to take n to the n power, let me just do this, and divide by the biggest power of n. So in other words, I'm going to, I'll write it as a reciprocal, multiply by 1 over n to the n. And then I'll come up here, multiply by 1 over n to the, n. Okay? That's really sloppy. Let me try that again. 1 over n to the n. Okay, so no argument here. That's just 1. So we're not changing the ratio. Down here, n to the n over n to the n is 1. So we've got a denominator of 1. That's really nice. Up here, I have n plus 1 to the n power divided by n to the n. So I'm going to bring this into the brackets. So it's already raised to the n power. So if I bring it into the brackets, then I'm going to leave the power on the outside of the brackets. And so I can bring this into the brackets as just n. So if we think about this, there's my n plus 1 to the n power, there's my n to the n power. Okay, so just kind of a caveat here for just the numerator. That's like saying n plus 1 to the n power over n to the n power. Same powers, that'd be like 4 cubed over 3 cubed. 4 cubed over 3 cubed is just 4/3 cubed. So this is just n plus 1 over n to the n. That's how we're just doing. We're just using our power rules to rewrite that so that everything is inside the brackets. And so I'm going to further simplify this. I'm going to forget about this because we don't need the denominator to be 1 and we don't need to express that. I'm going to rewrite this as 1 plus 1 over n to the n power. Okay. And at this point, I still have an indeterminate form. If we put infinity here, I have 1 to the infinity. That's still indeterminate. Now, what that means is since I have a power here, I really have to call this I really have to say this, where we say y equals the limit as n goes to infinity of 1 plus 1 over n to the n, and then I can do the natural log of both sides. Take the natural log of both sides. And then go ahead and take the natural log of both sides and go through that whole L'Hopital's thing in the law of logs. What ends up happening is this ends up going to, because this is a derivation we did in the previous chapter on integration techniques and L'Hopital's. This ends up going to the value E, Euler's number. And we know Euler's number is roughly about 2.7, so that is bigger than 1. And if it's bigger than 1, that means we have that, we're adding successively larger terms, so we're going to have that infinite sum again. So we know that this diverges then because of the ratio test.